Welcome back to the Explainer. So, have you ever had that one classmate who somehow managed to ace a brutally hard physics exam, not by actually studying the physics, but just by, memorizing the patterns of the multiple choice answers? Well, it turns out our most advanced AI models do the exact same thing. Today, we're diving into some fascinating AI news. We're looking at a recent paper that literally catches a neural network acting like the ultimate lazy student during a 3D scanning task. And, even better, we'll see how researchers finally forced it to actually learn the material. So what exactly happens when an AI decides to cheat on a physics test? In this Explainer, we're unpacking a really cool study focused on long-range, single-shot fringe projection profilometry. Yeah, I know, it's a huge mouthful, but don't worry, we're going to break it all down. The core mystery here is just wild. Researchers discovered that an AI found a brilliant but totally invalid architectural hack to completely bypass the actual physics of 3D scanning. It completely tricked the developers, and catching it, well, that required some serious detective work. Okay, let's look at our roadmap for today. First, the long-range 3D problem. Second, how the AI cheats. Third, diagnosing the shortcut. Fourth, the PhiCalNet solution. And finally, key lessons for developers. We'll make sense of all the jargon as we go.
Section 1. The long-range 3D problem.
To really understand why the AI resorted to cheating in the first place, we gotta look at the extreme physical difficulty of this task. Single-shot fringe projection profilometry, or FPP, is basically a 3D scanning technique where you project a very specific pattern of light onto an object. Then, you use the distortion of those lines, the fringes, to calculate depth and shape. Now, historically, this is almost always done super close up, but the researchers here, they were trying to push this into the long-range regime. We're talking moving the scanner to a standoff distance of more than 1 meter. But here's the catch. Moving the scanner further away doesn't just make the image smaller, it fundamentally breaks the physics of the traditional single-shot approach.
Right, so pushing this scanning distance creates a massive headache for 3 main reasons. First up, we have the inverse square intensity falloff. Simply put, light gets exponentially weaker the further it travels, right? And that drastically lowers your signal-to-noise ratio. Second, this degraded, super noisy signal makes establishing a physical ground truth incredibly messy. And third, because it's a single-shot method, meaning it's only taking one image at a time, crucial fringe order information is completely absent from the image. That makes the whole calculation mathematically ill-posed. So to test this thoroughly, the researchers actually built a massive photorealistic synthetic dataset. We're talking 15,600 images across 50 highly detailed objects, all at a 1.5 to 2.1 meter standoff. Basically, they built a perfect, controlled sandbox to train their AI.
Section 2. How the AI cheats. When the team threw a standard, best-in-class UNet baseline model at this incredibly complex, ill-posed physical problem, the model seemed to just figure it out almost instantly. 14.54 millimeters. That was the baseline model's object mean absolute error, or MAE. Now, context is key here. In the world of long-range 3D scanning across a really diverse set of objects, an error margin of under 15 millimeters sounds genuinely fantastic. Seriously, if you're a developer checking your high-level metrics, you'd probably pop the champagne and call the project a massive success. But this seemingly solid number was actually a complete mirage. It was hiding a catastrophic flaw in how the model was operating.
Here's the actual culprit: shape prior shortcuts. Remember our lazy student analogy? Yeah, instead of doing the incredibly difficult math required to decode the phase of the light fringes, which is, the actual physical core of FPP, the AI model found a much easier way out. It realized it could just look at the 2D boundary contours of the object in the image, recognize the shape from its massive training data, and simply guess the 3D depth based on those known outlines. It completely bypassed the physical phase unwrapping step. It literally wasn't reading the light patterns at all. It was basically just playing a highly advanced game of shadow puppets.
Now, what's really interesting is how the researchers initially tried to fix this cheating. Usually, in machine learning, if an AI is acting up or ignoring rules, you just add a penalty to its loss function, right? You mathematically punish it for ignoring the physics. But listen to this quote straight from the study. A physics-informed loss that enforces the same physics as a soft penalty on a depth-regressing network yields no measurable gain. It's actually kind of hilarious when you think about it. The AI had already optimized its entire workflow around completely ignoring the rules. So trying to lightly penalize a model that has successfully short-circuited the whole test, it does absolutely nothing. The architecture itself was the problem.
Section 3. Diagnosing the shortcut.
So, since standard loss penalties clearly weren't going to cut it, the researchers needed to prove exactly how the architecture was failing. To catch the shortcut red-handed and rip it out by the root, the team deployed a really methodical process using 3 specific investigative probes. Step 1 was linear probing. This essentially peeks into the internal layers of the network to see what specific features it's actually extracting from the images. Step 2 was GradCam. That's a visual diagnostic tool that spits out a heat map showing you exactly which pixels the AI is paying attention to when making its guess. And step 3, this was the ultimate trap, a flat plane out of distribution test. Basically, they showed the AI a completely flat board, 0 recognizable 3D object boundaries, and asked it to scan it using the light fringes.
The results from those probes were absolute proof. When shown that simple flat plane, the UNet baseline completely and utterly failed. Because there were no object boundaries to copy, the model literally had no idea what to do. The mechanistic interpretability tools, combined with conformal uncertainty quantification, perfectly converged on this one single failure locus. The scientific conclusion was undeniable here. The network never learned phase decoding. It just never learned the physics it was explicitly hired to do.
Section 4. The PhiCalNet solution.
So how do you actually force an AI to stop taking the easy way out? Well, the crucial point is the structural difference between these two approaches. The original baseline UNet allowed the model to output depth directly. It was a straight line from the image to the final answer, which left the door wide open for the AI to bypass physics entirely and just guess based on shape. PhiCalNet, on the other hand, fundamentally restructures the AI's hypothesis space. Instead of letting it guess depth directly, PhiCalNet forces the network to output wrapped phase data first. Only then does a fixed differentiable calibration layer actually translate that phase into depth. By mathematically pinning that calibration layer in place, the shape prior shortcut is completely wiped off the optimization landscape. The AI literally cannot cheat because the only possible way to get the required phase map is to actually decode those light fringes.
And the results of enforcing these strict physical constraints? They are honestly staggering. By forcing the AI to play by the real rules of physics, PhiCalNet achieved a massive 3.3 times reduction in mean absolute error. That overall object MAE plummeted from over 14.5 millimeters down to a highly impressive 4.46 millimeters.
And the data proves the fixed worked perfectly under the hood too. Using that technique we mentioned earlier, conformal uncertainty quantification, researchers looked at what happens when you reject the top 5% most uncertain pixels based on a metric called snapshot disagreement. In the cheating baseline UNet, doing this only reduced the root mean square error by a totally irrelevant 3.5%. But in PhiCalNet, rejecting that exact same top 5% slashed the error by an incredible 64%. This proves that the only remaining errors in PhiCalNet are highly localized, totally predictable discontinuity errors at the physical phase wrap boundaries. The model is doing the real physics, and it actually knows exactly when it's getting confused.
Section 5. Key lessons for developers.
We've caught the cheat and implemented the fix, so let's zoom out and look at the broader implications here. These takeaways are an absolute goldmine if you're out there building AI for ill-posed physical problems. First up, architecture. Architectural constraints will always outperform simple loss penalties when you're trying to eliminate shortcut learning. If you use intermediate physical quantities, you absolutely must pin your calibration layers and freeze them during training. This is what prevents that gradient leakage into those lazy shortcut paths. Second, evaluation. Never trust your in-distribution test sets alone. Just don't do it. Always benchmark with aggressive out-of-distribution tests, kind of like that flat plane test we saw earlier. Make the model prove it knows the underlying mechanics, not just the shapes. And third, diagnostics. Don't just rely on basic metrics like mean absolute error. Get in there and use mechanistic interpretability tools and snapshot disagreement metrics to verify exactly why your model is arriving at its answers.
Which brings us to our final thought. We just saw how easily a seemingly high-performing model fooled standard metrics by, well, memorizing shadows instead of learning physics. And we saw that simply slapping a loss penalty on it didn't do a single thing. So if loss penalties aren't enough to force your model to play by the rules, you have to wonder, what shortcuts is your AI secretly taking right now inside its black box? Thank you so much for exploring this with us. Keep questioning those metrics, and I'll see you in the next explainer.